In physics channel, the topic of this video is solving problems on length contraction. Length contraction is one of the fundamental effects of the special theory of relativity. Let's do a quick recap of length contraction before we solve some problems on the topic. Lorentz and Fitzgerald had independently proposed that moving objects would undergo a contraction in a direction parallel to the direction of the motion before even Einstein proposed the special theory of relativity. So originally, length contraction was proposed to ensure that Maxwell's equation were Lorentz invariant, that is, they remain unchanged upon Lorentz transformation. The importance of length contraction was fully understood once Einstein came up with this theory of relativity. So it beautifully fit into the special theory of relativity. Now the expression for length contraction: an observer in a frame of reference S measuring the length of an object to be L naught in its own frame will measure a contracted length L for the same object along the direction of motion if it moves at a relative velocity u with respect to his own frame as given by this equation. Capital L is equal to capital L naught times square root of 1 minus u squared over c squared. Right? Here u is the relative velocity between the object that is observed and the observer who is in another frame of reference. C is the speed of light. L naught is the original length of the object as measured by an observer who is at rest with respect to the object, whereas L is the length measured by him when there is relative motion between the two. So the term within the square root can always be only less than 1, so the length is getting contracted here, right? Unless time dilation where time gets dilated, elongated, right? So now let's do some problems. Alright, the first problem is a rocket of length 40 meter is observed to be only 32 meter as it moves past Earth. What is its speed? So in this case, right, so from Earth the measurement is done, let's say. All right, so a rocket is moving past Earth. And it is moving at a velocity. What is the velocity is being asked here in this question. If the actual length of the rocket is 40 meters when it is at rest with respect to the Earth, is measured to be contracted only to about 32 meters. Right? So in this case, what is the speed? So simply length contraction formula has to be used. So in this case, L is equal to L naught times square root of 1 minus u squared over c squared. Here L is 32 meters rather, contracted length. L naught is 40 meters, the original length. Right, so if you do the math here, we get 32 over 40 is equal to square root of 1 minus u squared over c squared, and this is 4 by 5. That is 0.8. So you have 1 minus u squared over c squared is a square of 0.8. That implies 1 minus u squared over c squared is 0.64, and I can do here u squared over c squared is 0.36. Therefore u is 0.6 times c. So the speed of the rocket would be 0.6 times the speed of light. so that it appears to be only 32 meters to an observer on Earth, whereas its actual length is 40 meters. Right. Next problem. A 6 feet tall astronaut is lying parallel to the axis of a spacecraft moving at point 9c with respect to Earth. What are the heights of the astronaut as measured by an observer in the spacecraft and on the Earth? Right. So in this case, two heights are being asked, right? One is as measured by an observer in the spacecraft itself. The other one is as measured by an Earth-based observer. So let's just try to draw a small diagram for this as well. So let us imagine a spaceship, and it is, let's say, moving in this direction. So that would be the axis of the spacecraft, right? And suppose an astronaut is lying parallel to the axis like this on the spacecraft, and this is moving at point 9c with respect to Earth. An observer here can also measure the height of the astronaut, because on Earth, if the astronaut is at rest, his height was 6 feet originally. Now when he is traveling, what would be the height measured by this Earth-based observer? Suppose there is an observer standing next to him on the spacecraft. What would be the height he would measure? That is why, what are the heights measured by the observer in the spacecraft and by the observer on the Earth? Right, here in this case, the original height is h0, let us say, and that is 6 feet. Now, within the spacecraft, there is no change in the frame of reference, and the observer there would be traveling along with the object that is measured, right? So there is no change in the height. So in the spacecraft, the observer would not feel any length contraction. Therefore, he would measure the height of the astronaut to be equal to 6 feet only. But on the Earth, the Earth-based observer would see a contracted height, and that would be given by, of course, our equation h0 times 1 minus u squared over c squared, and in this case it is u is 0.9c. So I substitute the values. It is 6 feet times 1 minus 0.9c is 0.81. That is 6 times 0.19 square root, isn't it? So the height would be, if you do the numbers, 0.436. So it's 6 times 0.436. That would be about 2.62 feet. So that is the height of the astronaut as measured by an Earth-based observer. Right. Let's move to the third problem. Two observers are standing 10 feet apart in front of a conveyor belt as it moves with a speed of 0.5 times the speed of light, 0.5c. Each decide to paint a mark exactly at the same instant as the belt crosses in front of him. How far apart will the marks be as observed by an observer on the belt? So we can imagine that there is a conveyor belt moving. Let's say it is moving this direction at 0.5c, and there are two observers standing in another frame of reference, let's say yes, 10 feet apart. Now we can fix two frames of reference. So in this case, I am fixing a frame of reference where these two observers are measuring as S, and then where the conveyor belt moves as S prime. Right. Now, if the distance between two marks that these observers make is 10 feet, as given here, what would be the distance on the conveyor belt is the question here, right? Again, simple application of the length contraction equation will solve this problem, because this is one frame of reference S, where the proper length, so to say, of these two marks, the distance between these two marks here is proper distance or proper length is 10 feet. On the conveyor belt, it is another frame of reference we are fixing, that is S prime, and that is moving with a velocity 0.5 c with respect to S. Therefore, any length measured there would be contracted length. Therefore, that length is going to be given by expression L0 times 1 minus u squared over c squared, where u is 0.5 c and L0 is 10 feet. So L is equal to 10 times square root of 1 minus 0.25, 0.5 c whole squared, c squared get cancelled, so you have 0.25. This is L is equal to 10 times square root of 0.75, and that is 10 times 0.866, if I'm right. Yeah, so 866, that is, therefore L is equal to 8.66 feet. So a distance of about 10 feet measured in S frame of reference gets contracted to about only 8.66 feet if suppose an observer is traveling with the conveyor belt. An observer traveling on the conveyor belt, sitting and traveling, would measure the length to be only about 8.66 feet. Right. So that is the conclusion we can arrive at here. The next problem, an astronaut is standing in a spacecraft parallel to the axis. An observer measures the speed of the spacecraft to be about 0.6 c with respect to Earth, and the astronaut's height to be about 1.3 meters. What would be his height on the Earth? So again, it's about height of an astronaut. So we have a spacecraft, let us say, right, and then the axis of the spacecraft is like this. It is parallel to the direction which the spacecraft would move, and let's say there is some platform on which the astronaut is standing, and the spacecraft itself is moving at 0.6 times the speed of light with respect to Earth. Now on the Earth, an observer is measuring the height of the astronaut to be about only 1.3 meters. Now what would be his actual height? That is the question. That means here, whatever he is measuring, the Earth-based observer, this height is a contracted height or contracted length in our length contraction expression. And therefore, the actual length is L is equal to L0 times 1 minus u squared over c squared is our expression. U is 0.6 c. Here L is given as 1.3 meters. We need to find out L0. So L0 is equal to L over square root of 1 minus u squared over c squared, and that is 1.3 over square root of 1 minus 0.6 c squared, it cancel, you have 0.36 as the square of 0.6, therefore you have L0 is equal to 1.3 over square root of 0.64, 1.3 over 0.8. That would be equal to 1.45 meters. So the original length of the object is 1.45 meters. In this case, it is the height of this astronaut who is traveling in the spacecraft. So the actual height is about 1.45 meters if he were on rest on the earth and his measurement was made. But while he was traveling on the spacecraft, his height was measured to be only 1.3 meters by an earth-based observer. Right, so that is the solution to that problem. So let's try to move on to the next one. Right, this one is a rigid spherical ball in frame S is observed from another frame S prime as it moves with a relative velocity 0.5 c. Describe the shape of the ball as observed by an observer in S prime. Right, so here what we have is a spherical, rigid spherical ball, and in S frame of reference, this ball is at rest. Right, now suppose another frame of reference S prime, which is moving at a velocity u is equal to 0.5 c. An observer is there in that frame and trying to measure the object. What would he see regarding the shape of the ball? The first point is length contraction occurs in a direction in which the object moves. So if S prime is moving with a velocity 0.5 c to the right, with respect to S prime or the observer in S prime frame of reference, the spherical ball would be moving to the left with the same velocity in the opposite direction. That means it would undergo a length contraction along this axis of the ball. Because in whatever direction there is motion, length contraction occurs only in that particular direction. That is a direction parallel to the motion. So here in this case, the motion is towards the left in this direction, negative x-axis, so to say, in our this thing diagram, and that means there is going to be a contraction in that direction only. If there is a contraction in that direction, for this observer, the sphere would appear like this, somewhat like this, contracted in this direction, whereas the normal diameter would be there in this direction. So this direction it is kind of taking a what is called an oblong shape. That is how the shape of this spherical ball would change for an observer who is moving at a relative velocity with respect to the spherical object. Right. So that concludes the fifth problem. Let's move on to the sixth problem. How much time does it take for a meter stick moving at 0.1 c relative to Earth to pass an observer on Earth if it is moving parallel to its length? So the length of the object here in this case is in its rest frame 1 meter because it is a meter stick. So we have a meter stick. Actual length is only 1 meter in its rest frame, but now it is moving with respect to an observer on Earth. An observer on Earth is watching it move past him at a speed of 0.1 times the speed of light, 0.1 c. Now what would be the time, because how much time does it take for the meter stick to move past? Now in this case time is the distance, so to say in this case, over the speed or velocity. Now here distance is what we will mean by the distance. In this case the distance is nothing but the length of the meter stick, but it is not the actual length with respect to this observer. It would be a contracted length that he would be measuring. So in this case, therefore, the time is equal to L times L naught times 1 minus U squared over C squared over U. Here L naught is 1 meter, and therefore it is square root of 1 minus U squared over C squared over U is the time. Right? And that would be 0.1 c is given here as the speed, relative speed. So t is equal to square root of 1 minus 0.1 c squared. Of course, the denominator there is a u. So if that is done, then we get 0.995 over 0.1 times 3 into 10 power 8 meters per second, and that is equal to 3.32 into 10 power minus 8 seconds. So a meter stick moving at 0.1 c with respect to an observer on Earth would take 3.32 into 10 power minus 8 seconds to move past the observer on Earth. And that is because of the length getting contracted to about only 0.995 meters. Right, that is a conclusion we can give that. The next problem is an interesting one. It is about pions traveling at a speed of 0.8 c. So pions are traveling at a speed of 0.8 c with respect to the lab frame. If the distance that pions travel is 36 meters in the lab frame, what is the corresponding distance in their own frame? How long does it take for the pions to move through this distance? How many pions will remain at the end of this time? That is the question. So here there are about 32,000 pions that are moving, right? So how many pions would remain at the end of this thing if there were if they were moving at a speed of 0.8 c, right? So what is the actual length here? 36 meters is the actual length or distance. So let me call that as d naught, distance that the pions would move, 36 meters. Now this distance would get contracted because of the motion at 0.8 c, and therefore the actual distance that they should move is d, that is equal to d naught times square root of 1 minus u squared over c squared, where u is 0.8 c. So if you plug in these numbers, we get 36 times 0.6, and that would be only about 21.6 meters. So though actually the pions travel 36 meters in the lab frame, they would need to travel only about 21.6 meters in their own frame because of length contraction, right? And how much time would it take for these pions to do this? Again, the time in this case is the distance over the velocity, and the distance in this case is d. The velocity here is going to be u. So the distance is 21.6 meters over the velocity is 0.8 c. So 0.8 into 3 into 10 power 8. And if you do the math, you get 9 into 10 power minus 8 seconds. That is the time for the pions to move through a distance of 21.6 meters. Now, the pion's half-life is in their own frame 1.8 into half-life of pions. The question, it is 1.8 into 10 power minus 8 seconds, and number of pions initially is about 32,000. Now, how many half-lives are there compared to this time is the question, right? The total time the pions survive is about 9 into 10 power minus 8 seconds. How many half-life lives would be there? Number of half-lives is 9 into 10 power minus 8 over 1.8 into 10 power minus 8. That is exactly 5. So we have 5 half-lives for the pions before they decay. This case, right? Therefore, number of pions that would be left at the end of this is given by the decay equation, that is n is equal to n naught e power minus lambda t, where lambda is a decay constant. And lambda is given by 0.693 over the half-life, and the time here we have got is total time, right? That is 5 half-lives, so we can say that is 5 t half, and therefore lambda t in this case would be 0.693 over t half multiplied by 5 t half. That cancels these two things. Therefore, lambda t would be only 0.693 times 5. That is 3.465. Therefore, n is equal to n naught times e power minus 3.465. Our n naught is 32,000. Initially, there were 32,000 pions, so it is 32,000 multiplied by e power minus 3.465 is 0.0313. Therefore, the number of pions that would be left at the end of this is exactly about 1,000 pions. So that is the conclusion. Right, let's go to the next problem, 8.1. A meter stick is measured to be about 500 millimeters in length by an observer in another frame. Oh, okay, so the actual length of this is, it's a meter stick, so it is 1 meter. The length of this object is, in its own rest frame, is 1 meter. But an observer in another frame, so let us say it is in S frame, own frame. S prime frame is the one in which the meter stick is moving, right? So what is the length he is measuring? He is measuring only about 500 mm or 0.5 meters. So he is measuring only about half its original length in some other frame which is moving with respect to the meter stick. Now what is the speed, right? What is the relative speed? U. What is the relative velocity in this case? That is the question. First part. How long does it take for the meter stick to pass by her? She is standing here as observer in S prime. How long does it take for the meter stick to pass by her if it is moving parallel to its length in this direction if it is moving? So either you can assume that S prime is moving with respect to the meter stick, or meter stick is moving with respect to S prime. There is relative motion, and that velocity is to be found out now, right? Okay. So here L is equal to L naught times square root of 1 minus u squared over c squared is the formula to be used. The actual length is 1 meter. The measured L is only 0.5 meters. So L naught is 1 meter. And therefore, here we have square root of 1 minus u squared over c squared is 0.5. Or 1 minus u squared over c squared is 0.25. Or u squared over c squared is 0.75. Or u is square root of 75 is 866c. So this is the relative velocity between the observer and the meter stick. Okay, right. Now the question here is, how long does it take to go past her? That is time. Time taken for the meter stick to go past her is the distance measured by her. It is 500 into 10 power minus 3 meters, because it is given in millimeters as 500 mm, over the speed. Speed has been calculated as 0.866c. So 0.866 multiplied by 3 into 10 power 8. And this is the time. So the time is going to be found out as 192.45 into 10 power minus 11 seconds. This can be again rewritten as about 1.92 nanoseconds into 10 power minus 9. So it is 1.92 nanoseconds. That is the equation. Right. The next problem is again about a meter stick, right? A meter stick is moving at a speed of 0.8 c relative to a frame S. So what is the length of the meter stick as measured by an observer in S frame? That is, in its own frame, what is the length if it is moving parallel to its length? Okay, here I think there is a mistake here. No, it is moving with respect to S frame at 0.8 c. What is its length with respect to S? That is okay. So we have a frame of reference S, let us say, and meter stick is moving in another frame, that is, let us say S prime. We don't care about it, but the velocity here is u is equal to 0.8 c. That could be another frame S prime. Now, how much is the length measured if the velocity is parallel to its length? It is very simple. We have to use the length contraction formula. L is equal to L naught times square root of 1 minus u squared over c squared. It is L naught is 1 meter here. L naught is 1 meter because it is a meter stick. So L is going to be found out to be equal to square root of 1 minus 0.64, that is 0.8 c squared. That is 0.36. The square root of 0.36 is 0.6. So in this case, it is only 0.6 meters, the first part. But the next part, what is the length if it is moving perpendicular to its length? So the same observer is measuring now the meter stick to be moving perpendicular like this to its length. So the direction of motion is in this direction. The length of the meter stick is in this direction. So now no length contraction occurs along the length, but there may be a small length contraction along the width of this meter stick. But we don't have to worry about that because we don't have any information on its width anyway. So only about length we have an idea that it is a meter stick. So 1 meter length, whether that 1 meter gets contracted, that is the question. No, there will be no contraction. Therefore, the measured length is going to be 1 meter here again for an observer who is in S frame. The second part of this question has answer 1 meter only. Third part, what is its length if it is making an angle 60 degrees with respect to its velocity direction in its own frame? So let me go to the next page to do that. Okay, so what is this thing? 60 degree angle it is making. So let me get back to the question again. What is its length if it is making an angle 60 degree with respect to its velocity direction in its own frame? So the meter stick in its own frame has an angle of 60 degrees. So let us call that frame as S prime frame. In its own frame, meter stick is making an angle 60 degrees with respect to the direction in which it is moving. The frame is moving in this direction. What is the velocity? That is the question, right? If the angle is 60 degrees, right? Because the measurement is now carried out with respect to another frame S, right? For that frame S, the angle would be different because there is parallel motion, so the angle would be different for any observer in that frame. Now the question here is, the length of this meter stick has two components, one along the x direction or x prime direction in this case, x in the S frame, the other along the y direction, right? So if we call the two components as Ly prime and Lx prime in the S prime frame of reference for the meter stick. So let us write in the S prime frame, that is meter stick's own frame, the length of that object is, let us call that as only L. That would be square root of Lx squared plus Ly squared, because it is like the hypotenuse of a triangle. I'm using Pythagoras theorem here. So the L is equal to square root of Lx squared plus Ly squared. Of course, prime notation has to be used because this is prime basically. And given information is 60 degrees angle. So here the contraction occurs along this direction, Lx, Ly prime does not change, isn't it? So the ratio of this two sides, Ly prime to Lx prime, is going to be tan 60 from this triangle, right? This triangle, this is Ly prime, this is Lx prime, so the ratio is tan 60 angle. We can also write from that if this is L originally, we can also write Lx prime, that is the x component, or in the direction length along the x direction is Lx prime, that is going to be therefore the length times cos 60, because it's cos component parallel to the x-axis, so it is L 60 cos 60. Therefore we can say that it is a meter stick, right? So it is 1, L is 1, capital L is 1 meters. Therefore Lx prime would be only 1 cos 60 or only cos 60, that is half. So our Lx prime is half. Now for an observer trying to measure this Lx prime as Lx in his frame, which is moving at a relative velocity u, he is going to measure a contracted length for the same Lx prime. So the length as measured by an observer So for an observer in a parallel, moving frame frame moving parallel to the S prime, that is for an observer in S moving at relative velocity u, this length Lx is going to be a contracted length of Lx prime. So this is the length contraction formula that we have to use here. And therefore this is half we have calculated. Lx is Lx prime is 0.5 half, right? So we have Lx is equal to 0.5 into this is 0.6. Therefore, Lx is equal to 3 meters. Sorry, 0.3 rather, right? Sorry, 0.3 meters. So, along the x direction there is contraction, the y direction there is no change. So, the contraction along the x direction is from 0.5, it is reducing to 0.3 meters. The y direction no change, 0.5 remains as 0.5. So, if you are worried about the Ly prime, that is same as Ly, and that is both equal to 0.5 meters. So the meter stick has two components. Okay, its length can be visualized as two components made of an Lx prime and an Ly prime. The Lx prime gets contracted from 0.5 to 0.3. Whereas the Ly prime remains the same, 0.5 meters for the observer in other frame of reference. Right. Of course, the angle that this makes also would be different, but here we don't even have to go through that route. The 60 degree for the S frame, the angle of 60 degrees would be a different angle because he is in relative motion. But we don't have to concern ourselves with that. Here we don't have to go through that route to get the answer. The answer is much simpler. We can arrive at that in a simpler fashion. Let us move on to the 10th problem. The antenna of a spacecraft is making an angle of 10 degrees with the axis of the spacecraft. If the relative velocity of the spacecraft is 0.700 c with respect to the Earth, what would be the angle of the antenna as measured by an Earth observer? So we can draw a diagram here. So this is a spacecraft and it is moving at 0.700 c with respect to Earth. Now this is the axis of the spacecraft and that is the direction of the motion parallel to the direction of motion, and an antenna here is making an angle 10 degrees with respect to the observer on the spacecraft, an astronaut probably. Now what would be the angle for an observer on Earth? The same angle of the antenna. Here we can clearly see that the antenna length is like this. If we zoom in on that, and it has two components, one along this direction and another along this direction, and along the this component it is making a 10 degree. So let us take the vertical component here it is along the direction of motion as Ly, and the horizontal component in this case is Lx for the antenna. Because of the motion along the y direction, there is a contraction of this length Ly in the y direction. Okay. Therefore, an observer in another frame of reference, let us say on the Earth, it is an S prime frame, let us say, because the spacecraft is in another frame, S frame. From this frame, if he measures, he would measure a different angle. Please recollect that in the previous problem, I had mentioned that the meter stick making an angle 60 degree in its own frame, this angle would be different for this observer in S frame. We didn't bother to calculate that angle because we could arrive at the answer in a simpler way there. But here the question specifically asks for calculation of that angle. So here we are going to do that. Right, therefore Ly is going to change, contract to Ly prime. So Ly prime is therefore equal to Ly times square root of 1 minus u squared over c squared, whereas Lx prime is going to be same as Lx, which doesn't contract in this direction, no change in this direction. Contraction occurs only in this. Lorentz contraction occurs, length contraction occurs only in this direction. Therefore, we can write from what is given as tan 10, that is angle 10 degrees, it is making is a ratio of the two sides, so it is Ly over Lx. Similarly, in the S prime frame, we can write a tan theta is equal to Ly prime over Lx prime. Therefore, we can write tan theta is equal to our Ly prime is Ly times square root of 1 minus u squared over c squared over Lx prime is Lx. Now Ly over Lx we know is given as tan 10 degrees. So here tan theta is equal to tan 10 degrees multiplied by square root of 1 minus u squared over c squared, and that is going to be equal to .176 times square root of this is 1 minus 0.49, because 0.7c is the velocity, relative velocity. So that is 0.176 times square root of 0.51, that is 0.714. So the product here is 0.126 tan theta. Therefore, theta is tan inverse of 0.126. Theta turns out to be about 7.16 degrees. So that is the angle that the antenna would make for an observer in another frame S prime, moving with a relative velocity u is equal to 0.700 c with respect to the spacecraft, right? So that concludes some of the problems that we wanted to solve on length contraction. Thanks for watching.